Welcome to this episode of Into the Impossible from the Arthur C. Clarke Center for Human Imagination at the University of California, San Diego. In this episode, UCSD physics professor Brian Keating interviews professor and author Matthew Stanley. Professor Stanley teaches and researches the history and philosophy of science at NYU's Gallatin School of Individualized Study. He holds degrees in astronomy, religion, physics, and the history of science, and is interested in the connections between science and the wider culture. He's the author of Einsteins War, How Relativity Triumphed Amid the Vicious Nationalism of World War I, the story of how pacifism and friendship led to a scientific revolution. And now, into the impossible.
Today, it's my pleasure to welcome my friend and fellow physicist and seeker of scientific knowledge and wisdom and things beyond, Professor Matthew Stanley of New York University, on the Arthur C. Clarke Center's Into the Impossible podcast, which is a production of the Arthur C. Clarke Center. We've been having such events and podcasts for the last few years now, and I invite everybody to check us out at imagination.ucsd.edu. But today, I want to learn from my friend and colleague about his newest contribution to scientific literature and popular scientific literature, and also talk a little bit about his endeavors in popularization of science, namely his best-selling podcast, which is called What the If? And I want to get into that later towards the end when we refer our listeners to obtain more information about you. So first of all, welcome, Matt, and congratulations on the upcoming release of Einstein's War.
Well, thank you very much. It's a pleasure to be here.
So we've known each other for a few years now. You've been to visit here in La Jolla and San Diego, and I've met up with you in New York. I want to just give a brief taste, maybe an advertisement, not that NYU needs this, but for why the program that you run, an independent sort of studies program that you run or help to run at NYU, is so special and what its mission is and how you fulfill that.
Sure. So our unit of NYU is called the Gallatin School of Individualized Study. And what we do is provide a space for students who have things they want to pursue and study that don't fit in well to traditional disciplinary structures. So sometimes that means students who are interested in multiple things that they want to find some way to bring together. So for instance, I've had students who want to study physics and philosophy. Right. And then other sorts of students we have are ones who want to study something that doesn't quite fit anywhere. So for instance, students interested in the nature of consciousness. So they'll need to know some philosophy and neuroscience and psychology, but none of those departments are quite right. So students come here and they work really closely with us as advisors, and then they get to take classes everywhere in the university. And we teach them how to think in this sort of interdisciplinary and innovative way to pursue their own interests.
And how long have you been affiliated with that program? How long has it been in existence?
11 years now, I think.
Okay. But your training is as a physicist, right? It's you didn't start off.
That's right. Yeah. So I started off in physics and astrophysics. I built lasers. And then got interested in the humanities kind of by accident, and discovered slowly that while I was really interested in science, the sort of questions I was interested in science weren't ones that I could really answer in the lab, but rather I needed to kind of change my point of view. And that's when I discovered that such a thing as history of science existed. And that's where I've been spending most of my professional time lately.
And when we first met back, I think it was 2016, you were at that point engaged sort of in your endeavors related to your current book, which is about Einstein, nationalism, and World War I. And if I recall, you were starting to flesh out those ideas as long ago as then, maybe before. So maybe you can talk to me about what made you inspired. You've written about Science and Religion before. This book is completely different from that, and I thought it was a delightful read amongst, I've been asked to read 3 or 4 books this year, and you'll explain why for the audience, why this year, 2019, is so significant, both in the history of science and particularly Einstein studies, almost an industry unto itself. Can you talk a little bit about how this book differs from your previous books? Maybe talk about your first books, and then we'll segue into Einstein's War.
Sure. So my first 2 books were academic books, so written for a small audience on specific topics. And the particular issues I was interested in were, as you say, science and religion. And I was particularly interested in this question of how it is that an individual scientist could hold their own religious beliefs and practice their faith and still be sort of productive scientists. So I wanted to, because that's a dichotomy that a lot of people think of as very difficult, if not impossible. So I was curious how that actually worked. My first book was about this guy, Arthur Eddington, who was a Quaker astronomer, and he's an important part of Einstein's story, as we'll probably talk about in a bit. So he's deeply religious, but also extremely liberal and modern and highly scientific. So I was interested in kind of how that played out in his work. What he's best known for today is events he did almost exactly 100 years ago now. Let's see here, we're 15 days shy of 100 years, when there was a solar eclipse. And he went to this little island off the west coast of Africa to test a prediction that Einstein had made, which was that the gravity of the sun could bend light. And this was going to be the definitive test of Einstein's theory of general relativity. And this, the general structure of this story is fairly well known. It appears in textbooks and so on. And this is sort of the moment that makes Einstein as we know him. That is, he's an obscure German physicist that very few people had heard of. And then almost overnight, as these results get announced, he becomes the most famous person in the world. But one of the things I found interesting as I was researching Eddington was realizing how much of this story was bound up in World War I. So this happens right after the end of the war. It's actually before the formal peace is declared. So the guns have stopped, but Germany is still under blockade. So I was really fascinated to see how much of the story of Einstein becoming famous was tied up with these political questions during the war.
And so it's no strange, Einstein was, of course, no stranger to politics. Even in his early career, he was sort of targeted for semi-radical views during following his miracle year, where he discovered the so-called special theory of relativity, leads to the most famous equation in physics, which is E equals mc squared. But he really didn't achieve the worldwide fame, and he certainly didn't receive the international recognition for one reason or another until after these events, right, that are described in this book. Can you sort of maybe speculate on why this is, and maybe talk about the fortunate turn of events that for Einstein in retrospective that led to him basically receiving this attention, whereas if he had been, if the eclipse had occurred a couple of years earlier, that he possibly would not have, or did occur a couple of years earlier, but the expedition failed for reasons that I'd like you to get into. But maybe speculate on what alternative history, counterfactual, as your show often likes to get into.
Yeah, so it's kind of a funny thing to think about World War I as being fortunate for anyone, but it certainly was for Einstein. So Einstein, as you say, he's been working on relativity since 1905, but it isn't until 1915 that he finishes general relativity, sort of his magnum opus. And we might think that this would have been sort of an extraordinary moment for world science, but in fact, almost no one knows about it. Partially this is because Einstein just isn't a very important person, but more important is that Germany is under blockade because of the war. So the Royal Navy is preventing any ships from coming or going to Germany, and then there's the trenches on land. So scientists had stopped sending scientific communications back and forth between enemy countries. So essentially, other than Einstein's friends in Berlin, very few people even know he has finished this theory. So what should have been this extraordinary moment is sort of this tiny little quiet thing. And what happens is that Einstein, as you mentioned, is no stranger to politics, and he's a socialist, and he's on the political left. And he's under a lot of pressure for that within Germany. So he's a pacifist, trying to bring a halt to the war. But he's deeply uncomfortable being in the German capital as the war is raging. So he cultivates some friends in the Netherlands, which is a neutral country during the war. So he finds other like-minded physicists. So these are people like H.A. Lorentz, Willem de Sitter, Paul Ehrenfest. So Einstein goes to this little town Leiden in the Netherlands, and that becomes sort of a center for the study of general relativity, in large part because Einstein's friends are there. These are people he's happy to sit around with and play the violin and talk politics as well as talk physics. And so one of those folks, Willem de Sitter, decides that more people should know about Einstein's new theory of general relativity. So he sends a letter to London with sort of a capsule summary of this new theory. And it gets opened by this one person, Arthur Eddington, who's really important for two. It's really important that he's the one who opens that letter for two reasons. The first is that he's one of the few people who can read non-Euclidean geometry, right, which is the format in which Einstein's theory is written. And second, and more importantly, because he's a Quaker, he is a pacifist. So he thinks the war is terrible, and he's very excited to the opportunity to sort of create this English-German connection through science, literally over the trenches of the war. So Eddington takes up sort of the cause of Einstein and relativity, both because of its scientific importance and because it's sort of an opportunity for him to show how science can transcend sort of the worldly strife of the war.
And so it becomes sort of a respite from that. So you look back on a series of events that had to occur in order for relativity to get tested when it did 100 years ago. It was also there was an opportunity that Einstein had to, and he agitated for, to have his theory tested, sort of the 1914 eclipse. And that ultimately proved unsuccessful, even though I think technologically it would have been important. I do, as an experimental astrophysicist, I would like to talk to you about some of the notable controversies or controversies, perhaps, as Eddington might say, that surround even the interpretation of the results to this day. But there's another serendipitous, fortuitous event which took place, which was essentially the World War One. Again, it's another the actual events of World War One that led up to preceding the 1919 eclipse. So there were expeditions.
Right. So in 1912, sort of an early version of general relativity, Einstein had realized that there would be this gravitational deflection of light, and he had a number he was looking for. It's about 0.8 arc seconds. And so based on that, as soon as he gets his job in Berlin, actually, he manages to get friends like Max Planck to conjure up the money to pay for an expedition to go observe, to look for this prediction at the August 1914 eclipse, which happened to be in Crimea, which was part of Russia at the time. So a friend of Einstein's, a young man named Erwin Freundlich, is in charge of the expedition. And they go out and they set up their equipment. And I should say there's a number of expeditions there. That's, solar eclipses are rare enough that everybody sends teams when they can. Mm-hmm. And they were days away from the eclipse when the war breaks out. And all of a sudden, Freundlich and friends are no longer German scientists setting up their telescopes. They now look like enemy spies setting up surveillance equipment near a major Russian naval base. So they're all arrested as spies. Their equipment is impounded. Freundlich is actually released miraculously in one of the first prisoner of war exchanges of the conflict. And Einstein, of course, is devastated because he's sort of laid everything on this measurement, right? This is how he's going to convince people that relativity is right. And then about a year later, he discovers that he had made an error in his calculations. And the deflection is not about 0.8 arc seconds, it's about 1.7. So it's this great irony that if the war had not happened, then Freundlich would have done the observation and been looking for the wrong number. So if he had done the observation well, that would have been seen as evidence not for relativity, right? So Einstein has a number of extremely lucky events during the course of the war.
So one of the things that really stood out to me, I don't know if you had an opportunity to view the total solar eclipse of 2017, the so-called Great American Eclipse.
I did, from Idaho, yeah.
Ah, good. Yeah, so I was on the East Coast and you were closer to the West Coast. And when I was observing this, first of all, it was very difficult to get my, then 4-year-old out of the car to even witness it because he was kind of grumpy and he didn't want to get out. Why is it getting dark in the middle of the day? But I got him out, and then he was going crazy. It was this, quasi-religious experience, and for him, and kind of this sense of awe and vastness of the universe. Mm-hmm. But when I was witnessing it, I was sort of overcome with a different type of awe and curiosity, which was, I don't see any stars that are even, plausibly within reach of the eclipse. Now, there's another piece of fortuitous happenstance, if you will. Some say, X-Files would say nothing is a coincidence, right? But if you look at where the eclipse took place celestially in the 1919 eclipse, it took place in a very rich field of background stars known as the Hyades cluster, and had it been observed in 1914 or 1912, I guess, no, 1914, it would have been a much poorer background, probably closer to the background in which it was seen in 2017 from the USA. So I wonder, when that eclipse took place, I must confess, I was, looking at the corona, but I saw, maybe one star with the naked eye. And then you think, well, that's, nowadays, we have CCD cameras, but even, the degree of technological sophistication currently, I have one student who I would trust with a solar expedition to take an optical picture, and they did, and I got many, many views of this picture. But there were no stars, and so can you talk a little? You talked a lot in the book about the logistical lengths to which astronomers had to go. International travel over months and time. And I have to say, it still boggles the mind, and for that reason, hopefully, we can get into some of the doubts that maybe still persist. And I think that they're more well-placed than, say, doubts that the Earth is a sphere, or or that the sun, doesn't go around the Earth, etc. So I wonder, if you can talk a little bit about the from a physicist and a former, recovering astronomer and current physicist. What do you make of the technological?
So I should say it's a fantastically difficult measurement to do for a whole bunch of different reasons. And as you suggest, the 1919 eclipse was very fortunate for a number of physical reasons, right? So one of them was right in front of the Hyades. So you've got a nice cluster of bright stars that you can look for. It was high in the sky. And when you're looking for precise measurements, a little less atmosphere to go through counts for a lot. And it was 6 minutes long, which is really long for a total solar eclipse. So they were able to take lots of good photographs. And those conditions just don't happen very often. And Eddington actually talks about this when making the case for the expedition back in 1917 and 1918. He says, we will have to wait 300 years until conditions are this good again. So, let's get it right this first time. In terms of stellar visibility, this was a real struggle for Einstein and Eddington and everybody at the time. So as you say, they're hard to see with the naked eye, particularly if the eclipse is close towards the horizon, because the slightest bit of atmospheric distortion ruins it. And it also depends enormously on the state of the corona. So if the corona happens to be expansive and bright in that quadrant of the sky, then it'll wash out any stars you can see. In terms of photographs, the equipment that you usually use to take a good photograph of the corona or of a solar eclipse is not good for picking up on small images like stars. That is, use a different optical setup. So this was one of Einstein's early problems. So early on, when he realizes there should be this deflection, his first thought is not, let's go send an expedition, because that's really hard to do, and you have to wait for an eclipse. But let's just look at old eclipse photographs and see if we can see the deflection there. So he writes to all the astronomers he knows, and they write to all the astronomers they know. The query actually gets all the way to Mount Wilson. And nobody has any good star photographs. And the reason for that is just because nobody cared, right? That's not what you look for. It's not what you set up your optical equipment to try and record. So there were a few kind of accidental captures of stellar images, and that's how they ended up deciding what telescopes they should bring. So they end up bringing not the kind of photograph, not the kind of telescopes you would normally use for a solar eclipse observation, but an astrographic, which is what you use for fine stellar measurements at the time. Mm-hmm. And I should say one of the things that came up a lot, and still comes up a lot too, is the scale of the measurement, right? So 1.7 arc seconds comes out to be about 1/60th of a millimeter on a photographic plate. And depending on your field of technical expertise, that might seem absurdly small. Right? Say, how can you reliably measure 1/60th of a millimeter? And the astronomers at the time sort of shrug their shoulders and say, we do this every day, right? That's a pretty big stellar parallax, and we can measure those fantastically precisely. So for astronomers, they'd been doing this for decades. And it's kind of interesting to see the skepticism from even like experimental physicists who say 1/60th of a millimeter is far too small to measure, and the astronomers say, it's no big deal.
Yeah, the thing that struck me is that they also had to take images when the sun is on the other side of the constellations of the zodiac in this case, and that they had to preserve those plates also under pretty controlled conditions. I mean, this wasn't, you download it to your laptop and click on a couple boxes. And even nowadays, it's not, as I say, it's really not so easy. There are a lot of subtleties in measuring star positions, and it's, left as an advanced, kind of exam topic almost for advanced undergraduates, at least, to actually try to do this with the CCD, and maybe even show you cannot do it with certain CCD cameras. Most CCD cameras are not. Most telescopes aren't able to do this. But then that, as I say, is with a telescope, not a piece of film, an emulsion that has to be preserved and kept over, 6 months or more years before. And it was just remarkable how soon after the eclipse, the results were published, of course, to great fanfare. And you talk a lot about this in the book as sort of this early version of, kind of social media or social proof that really, by virtue of the abstractness of the underlying physics, served to make Einstein a celebrity and perhaps, really amplify his advocacy for things such as political views. So I wonder, is this, in your mind, I mean, have there been other examples where, kind of science and politics so directly intersected, both either for good or for bad? I mean, later on, Einstein would advocate for atomic weapons, and he would use the fame, I think, that he had gleaned from this episode. But how often has science and politics, really been intertwined in this way?
Almost always, I think, is sort of the answer. Surely, as the world gets more globalized in, say, the middle of the 19th century, the issues are more significant just because information can be spread more rapidly. But simple things like the metric system, for instance, or where the 0 degree of longitude is, which nowadays we think of as fairly trivial, were unbelievably politically fraught conditions. So for a very long period of, for instance, there were 2 0-degree longitudes, right? There was one that went through Greenwich and there was one that went through Paris. And which one you chose depended on your national allegiance. So if you were in the United States, say, you had to choose, right? Were you on the French side or were you on the British side? And those had quite extraordinary consequences.
And talk a little bit about the, kind of shift in worldview that was ushered in after the eclipse. So, one of the more remarkable aspects of Einstein's theory of general relativity. So Einstein had 2 theories that both have the name relativity in it, and the theory of general relativity subsumes the theory of special relativity, which, as I said earlier, it deals with the interrelationship between matter, mass and energy equals mc squared, the constancy of the speed of light, aspects of bizarre aspects that are completely unfamiliar to our everyday life, such as length contraction and time dilation, none of which we ever perceive, or human beings don't perceive. But then general relativity, which subsumes special relativity, actually, in some sense, is more easily interacted with on one hand, and then, of course, much more abstractly related in others. So in my mind, there are aspects of relativity which are really simple, and you do a beautiful job explaining in the book, such as the principle of equivalence, which are another form of relativity. And I should say the term relativity, or the concept of relative motion of objects, goes back to Galileo, and probably before, but he was the first to really champion it in the famous dialogue on 2 world systems, where he talks about a boat in motion, and then inside the boat, where you can't see the outside ocean as you're moving, birds will fly around and bugs will fly around, and they have relative additive velocities with respect to the water and so on. Well, Einstein turned that on his head when he said that the speed of light was constant and so forth. But you talk a lot in the book about the principle of equivalence, which in some sense, is as revolutionary as the constancy of the speed of light. And I wonder, was that taken as, the scientific canon, before? I mean, that doesn't depend on the eclipse being right, or even the,
right,
curvature of space-time being warped by matter that we'll get into. But none of that depended on it. So is there any, was that taken for granted, or was that really kind of controversial, the principle of equivalence?
So the equivalence principles, I think, have a fascinating episode, particularly in the history of relativity, but also in the history of science generally, in that it's extremely accessible. So you can do the major convincing of the principle of equivalence just sitting in your chair right now. You just have to kind of think differently about watching things fall and think about how you feel things. It was not a major thing unless you were someone like Einstein, and specifically someone like Einstein who subscribed to the work of Ernst Mach, who was a late 19th century physicist and philosopher. And Mach had sort of a philosophical perspective on science that's nowadays called positivism. And the stress of Machian positivism is put on direct measurement. That is, any category and any kind of scientific ideas or categories you have, you should track back to how you directly physically measure it and experience it. And it's that kind of Machian thinking that gives rise to special relativity in 1905. So the equivalence principle is sort of an extension of that kind of thinking. But not many people were thinking that way. I think it's one of the things that really makes Einstein distinctive, is he has this kind of critical approach to the categories of science. So when he's wondering about gravity, his first thought is not to write down a new equation or set up a laboratory experiment. Because he's a Machian, he says, how do I feel gravity? How do I know that gravity is pulling on me right now? So people who were interested in those sorts of philosophical questions about science were very impressed by the equivalence principle. Everybody else said, that's fine, but come back to me when you have an experiment we can do.
Right. And of course, it's very difficult to do experiments when you require masses on the order of the sun, or, much, much greater masses. But as you point out in the book, it is sort of still pertinent. Effects of general relativity, in addition to purely sort of philosophical and going back to, Galileo, et cetera, they are at work in your pocket. The fact that the local space and time interrelationship is affected by mass is built into every cell phone, that has a GPS receiver within it, because without those corrections that are due to fundamental general relativistic properties of space-time curvature via the matter associated with it, we would not be able to navigate anywhere. Well, I'm not able to navigate super precisely. I've told you before. I turn off the voice of navigation in my car, so I don't have two women yelling at me that I can't drive, which is usually true when I'm with my wife. But the notion that it's somehow esoteric or just pie in the sky, literally, I think is really, you make a beautiful case how it really affected not only science, and for scientists, but actually eventually the general public as well.
Yeah, so the applications of general relativity, which, as you say, nowadays we're literally surrounded by, take a long time. In even sort of applications within science, it isn't until well after World War II that people are applying it to things like cosmology on a regular basis. So before that, the impact of relativity is sort of purely philosophical and social. Nobody has a GPS in their pocket in 1919. But what they do have is a worldview that had just been shattered by the war. Right? There had been 4 years of industrialized slaughter on the kind of scale that no human being had ever seen before. People were doubting everything. This was also the era of the Russian Revolution. So when people when people at the time talked about revolution in science, they were thinking about revolution in political terms, right? They were thinking about governments being overthrown and societies shattered. So that's sort of the framework that people are thinking about relativity in. So Einstein, kind of as a word, becomes shorthand for any kind of upset hierarchy and destroyed order and inverted ways of thinking about the world. And so he's both sort of simultaneously this great icon of hope and peace and internationalism, but also sort of a threat to what everyone thought they had already known about the world. And I think it's that kind of pull in two directions that really brings Einstein to the fore and makes the average person care about him, even though they don't understand the science at all.
Yeah, you mentioned the milieu in which he was involved. And of course, one of the great philosophers of the day, Karl Popper, was also kind of opining at that time in an attempt, I believe, to, sort of replicate what Gödel eventually would do for mathematics, which is, prove an incompleteness, a crisp test to define, what is mathematical, what is not mathematical. And then, of course, Popper comes up with his falsificationism, I think you call it in the book, criterion, which is maybe something you can get into. And I'd like to discuss with you how it's made a resurgence in some fields, including my own, which is the investigation of the multiverse and fine-tuning and all sorts of things. So can you explain what was Karl Popper's obsession with falsification, and maybe how did it intertwine with politics back then? Because he was a pretty...
Sure, yeah. So this is an interesting kind of side element of the story. So Karl Popper's a young man. He's, I think, 17 when Einstein becomes famous. So he's Austrian. He's too young to have fought in the war, but he's very interested in science, and he's a Marxist. And this is important for a couple of reasons. So one of the things that Marxists, at least at the time, made the case for was that Marxist philosophy sort of predicted a certain series of political and economic developments in the world. That is, capitalism would collapse onto itself, and then Marxist societies would appear from the ashes of that. And one of the things Popper found was that any event that happened in the world would be seized as evidence that Marx was correct. So on one hand, that's super powerful, right? Every revolution, every war said, well, that's just what Marx would have predicted. But he was sort of unsatisfied with that. And at the same time, Freudian-style psychoanalysis was becoming popular as well. And that had a similar feature, which is there were rules for interpreting dreams. And any dream you have, a Freudian can explain to you in Freudian terms what that dream meant. So again, very powerful. But Popper was sort of unsatisfied. He was worried that these theories were too powerful. That is, if you could always find evidence to support your ideas, wasn't that some kind of problem? So then Einstein comes along, and what he's impressed with by Einstein was that Einstein liked to say, not just if there's gravitational deflection, then relativity is true, but he liked to say it as, if there is no gravitational deflection, relativity is not true. And Popper said, that's what science must be. That is the willingness to be proved wrong, because with both the Marxist and the psychoanalysts, there was no observation that would convince them they were wrong. So Popper uses the example of the 1919 eclipse as sort of the perfect example of science. You put a bold theory out there and explain how it can be wrong. So as anybody can be right. It's very easy to massage information to make it look like you're correct. It's much more risky and therefore more impressive, he says, to set out the ways you could be proven wrong. This comes to be called falsificationism, this idea that the essence of science is not proving an idea right, but proving bad ideas wrong, and then eventually you're just kind of left behind with the best explanation that has survived all the tests so far. And I should say, this is a very handy way of thinking about science, because it's fairly easy to sort things into falsifiable hypotheses and non-falsifiable hypotheses. And the reason it gets this resurgence in the 1960s is actually as part of an attempt to fight back against what nowadays we call pseudoscience. So this is sort of the emergence of creation science and Velikovskyism and Erich von Däniken style fringe scientific ideas. So actually it's people like Carl Sagan and friends who pick up Popper as a useful tool for saying these ideas are not scientific as well. And as you suggest, nowadays, it's become important again in cosmology, I think largely due to the many worlds hypothesis and some people suggest inflation as well. And then, of course, string theory. So the question being, what are the observations that can prove those ideas wrong? That is, are they falsifiable in Popper's sense? And one of the fact that it turns out it's actually not so easy to apply Popper's ideas to these sorts of things. That is, we have vigorous arguments about whether multiple universe theories are falsifiable or not. And this is one of, I think, the difficulties of Popper's theory, is that it looks like it should be easy to apply, but in practice, it turns out to be quite difficult.
Yeah, and as I often like to point out, two of the things that Popper, derided as non-scientific or unfalsifiable were astrology and, Marxist, dialectic materialism. And, if you look at your local newspaper, you'll find, astrology is alive and well. And you can,
so it's not going anywhere
any time of day or night. And Marxist socialist, there are many more countries that are, Marxist socialists that still endure to this very day than Popper could ever have dreamed of. What was so, kind of interesting to me is how, yes, it has resurged in this description of what is real science, especially with regard, as you say, string theory and the concomitant potentiality of multiverses and inflation. I want to just close in the limited time we have left with one, just as a nerding out opportunity with a great sage like yourself. The eclipse was sort of it had all the great elements. It had a great story. It had a literal cosmic event. It's not something like the LHC turns on, it runs for a couple of years, it collects 5 data points, that are not ruled out by some other man. Then the Higgs boson is there, and there's a probability of 1 in 3 million that it's a fluke. But this had the sun, being eclipsed by the moon. These are things that were, foretold omens back in the past. It just had all the greatest and risky events that had almost proven fatal in certain cases.
Mm-hmm.
And so it had this wonderful power of authority and story and all these biases built into it. And I think a lot of people feel scientists are not susceptible to biases. I personally do think, I don't want to bias your answer, but you can take for with the grain of dust, what level of authority I am. But what do you think about this notion that scientists are sort of this infallible, unflapping pursuers of truth, and that we aren't subject to biases? You often hear that. Well, religious people.
Yeah.
Just believe in stuff based on faith, but science is always based on reason, and et cetera. Where do you stand in this discussion?
So I think it's actually quite dangerous to think of science as a perfect, purely rational system of producing knowledge. And this is what I mean by that, is that's what we're taught in elementary school. But that's not the case. And it's not hard to find examples in which scientists are real people, right? They have political beliefs and religious ideals, and they have friends, and they have enemies, and they make mistakes, and they have flashes of insight, right? And if you think that, if you're sort of raised on the idea that science is, by definition, is a purely rational, entirely empirical enterprise, the first time you encounter one of those real people situations, your faith in science is easily broken. Right. Mm-hmm. And this is something I see with my students a lot. That the first time they hear Jim Watson saying something sexist and racist, they say, "Oh, well, scientists aren't perfect after all. Why should I believe any of them?" But if you accept right from the start that science is a distinctly human enterprise, full of messiness and desires and beliefs, then I think not only is it much more robust against those sorts of criticisms, but I think it's also much more interesting. Right. So for the story in my book, if you think Einstein just sat down one day and wrote out the equations of general relativity, and then somebody just went out and proved it, that's a very uninteresting version of science, right? And I think it would be hard to get people excited about going into science if that was the kind of thing it was. But if you point out that Einstein is trying to keep himself from starving to death at the time and has to talk his way past border guards at the Swiss border crossings. And Eddington is trying to keep himself out of prison for being a pacifist. At the same time, he's trying to set up this globe-spanning expedition. It seems to me that that's a much more compelling kind of industry to join up with, right? A place where you can really ask cosmic questions and meet interesting people and draw on all of your skills, right? It's important to be creative and social and insightful, along with being good at math and knowing how to tighten a micrometer screw.
Right. Yeah, it always troubles me when people say, "Oh, I'm not a scientist," and no one would ever say, "I don't know English. I'm not very smart." I mean, otherwise educated people, obviously. So it was really, truly a delight speaking with you today, and I can't thank you enough for your time. And I share in the excitement. Not the least of which because I am actually mentioned in the back of your book, which I didn't expect. But I am very happy to take that little bit of credit that I might have earned along the way. It's great to hitch your wagon to a star like yourself. So I want you to just spend the last couple minutes maybe talking about where people can find you, the book, any websites, and then just a minute about your podcast with Phil Shane.
Sure. So the book is Einsteins War. It's available for pre-order on Amazon now. I'm not sure when this will be airing, but the book is officially out on May 21st. It's available in hardback and ebook and audiobook, for which I did the narration too. So if you have been able to stand my voice for the last hour or so, then you should pick up a copy of that.
Mellifluous voice.
My email is matt.stanley@nyu.edu if you want to drop me a line. But otherwise, my public face is through the What the If podcast. That's whattheif.com, which I co-host with my friend Philip Shane, a documentary filmmaker, where we change something about the universe and try to figure out what the consequences of that are. It's sort of half popular science, half science fiction improv.
Yes, it's really, truly a delightful podcast. I've been lucky enough to go on it a couple times and hope to be on it again and have you back on the Arthur C. Clarke Center for the Human Imagination's Into the Impossible podcast. This has been a production of the Arthur C. Clarke Center at UC San Diego. And I want to thank you, congratulate you, and wish you the best of luck, Matt, with all your future endeavors, especially this wonderful book, Einstein's War.
Thank you so much. I'm really appreciative of being here. Happy to come back anytime.
Thanks.
This has been Into the Impossible, a podcast of the Arthur C. Clarke Center for Human Imagination at University of California, San Diego. We'd like to thank our guests and acknowledge our generous patrons and sponsors, including Viasat Inc., members of the Founders Orbit, and the James B. Axe Family Foundation. Your support is appreciated. Find out more about the Clarke Center at imagination.ucsd.edu.